Welcome to today's deep dive. We are treating this session as a technical slide deck presentation tailored specifically for you, the professional plant designer.
Yeah, our mission here is to walk chronologically through the engineering guide for sizing jaw, cone, and impact crushers.
Exactly. So on this first slide, we see the foundation of plant design. The bottleneck principle. Think of a processing plant like a multi-lane highway. Traffic only flows as fast as the narrowest lane.
Right, the bottleneck reality. It's pretty simple math. If you have a 600 ton per hour primary jaw feeding a 350 ton per hour secondary cone.
The plant's true capacity is just 350 tons per hour.
Exactly, strictly 350. But people ignore this and fall into what we call the CapEx trap. They size one stage larger just to be safe.
Which is an expensive habit.
Oh, massively. You end up exponentially wasting capital on these massive steel motors. Like, you're jumping from a 200 kilowatt motor to a 315 kilowatt motor.
Wow.
Yeah, and you're paying for electricity that never actually converts to product.
Well, moving to the next slide, looking at the flow sheet turn, you have to push back a bit. If downstream stages see only a fraction of the initial run-of-mine feed due to bypass screening, isn't it financially safer to oversize the primary jaw anyway?
I get why you'd think that, but no. You're just engineering a bottleneck on purpose. That bypass material still leaves a fixed volume hitting the secondary stage.
Right.
So an oversized primary jaw just creates this larger, faster surge that the downstream equipment physically can't swallow.
Ah, I see.
Yeah, your expensive primary motor just draws inefficient idle power while waiting for the cone to catch up.
Okay, so moving to the next slide, we evaluate reduction ratios and sizing paradigms. Contrast the single pass reduction ratios for me. We're looking at jaw at 2 to 3, cone at 3 to 5, and high velocity impact, or HSI, at an incredible 7 to 10.
Yeah, the HSI ratio is wild. It's a completely different mechanical approach.
So sizing a jaw relies on pure math, like the 1956 Rose English formula, right? And cones rely on empirical lookup tables based on closed side settings.
Yeah.
But impact crushers, are they essentially just physical crash testing?
Pretty much, yeah. You're throwing rocks against anvils, but there is a severe trade-off there.
Because of wear and tear.
Exactly. Achieving massive reduction via kinetic energy works, but if the material is highly abrasive, say over 15% silica content, it causes severe wear costs. You literally destroy the machine's internals.
Which perfectly sets up our next point.
All right.
On this final slide, we combine these paradigms into the master selection matrix. So machines must be selected by physical constraints, like that maximum feed size and the SiO₂ content, before refining for capacity or cubical product shape.
You have to respect the kinetic limits. Take jaws, for instance. If you exceed 85 to 90% of a jaw's critical speed, you don't get more capacity.
You don't?
No, the rock doesn't have time to fall. You just churn the material in place and spike your bearing temperatures.
Oh, that sounds like a maintenance nightmare.
It is. And for HSI, if you double the rotor speed, you double your capacity, sure. But you multiply your wear cost per ton by a factor of 6 to 8.
Right, 6 to 8 times the cost? That destroys profit margins.
Instantly. It's brutal.
So quick question about the math. If the Rose English analytical formula gives us theoretical capacity, why do manufacturer catalogs rate the capacity much lower?
Well, catalogs have to build in conservative allowances for standard feed gradations. The theoretical math assumes a perfect world, but real rock is, messy.
Makes sense. Mastering these mechanical constraints is what prevents you from falling into the CapEx trap, allowing you to right-size your motors and maximize throughput.
Absolutely. It's the only way to design efficiently.
But I want to leave you, the listener, with a final thought to chew on. If future plants start using AI to monitor real-time wear and rock hardness, could the bottleneck stage dynamically shift from machine to machine during live operations?
Oh, like a moving target.
Exactly. And if it does, we need variable speed motors across the entire flow sheet just to keep up. Something to consider for your next plant design.